Hello, welcome to Business Statistics. The textbook that we're using is Statistics for Managers using Microsoft Excel. We are using the 7th edition, although there is an 8th or 9th edition, but mostly we're using the 7th edition because we write most of our Excel code as part of the course. So today we're going to be looking at Chapter 3 that covers numerical descriptive measures. Let me show you what we're going to be covering in the chapter. So we're going to learn how to describe the properties of data. Data has a central tendency, the ability to be center, measure of variation, and it has shape. We're going to learn how to numerically describe those three things. We're going to learn how to compute descriptive summary measures. How to compute and interpret a box plot. That's a special kind of graph that tells you how data is distributed. The idea being that if we know a little bit about data and can talk about the distribution of the data, then we can use a small sample to predict a population. And then we're going to talk about covariance and correlation coefficient. So let's start with the measure of central tendency and variation. The measure of central tendency describes the center of the data. There's several descriptors for central tendency and variability, but data has a center. It has an average value, and then it has a variation. Variation is the width of the data. The central value is the descriptor of the data. So if I came to you, for example, let's use a King's College student as an example, and I said, what is the average height of a King's College student? And you say something like 5.3. Well, that's useful information. But in your head, you're probably thinking that, okay, if that's the average, well, who is the tallest and who is the shortest and what is the range of the data, right? So that is where measures of variation come in. The average is great for describing data in general, but the variation gives more information about how wide or how spread out that data is. More than that as well, not only are you asking yourself, okay, how did we get to 5.3? What is the smallest value and the largest value in this data set? Your question should also include something like, how is it distributed? Because 5.3 seems small. It seems not too tall to me, right? So how is it distributed? Is it that the majority of students fall in the smaller bracket? I'm about 5, okay, not going to say. I'm about 5 something myself. So is it that everybody falls in that bracket and then there are very, very few people in the tall bracket? What is going on here? Or is it that we have a lot of people who are 3 feet, 2 feet? Maybe we're counting maybe we just have a whole bunch of people who are 2 feet tall in that group, but you need additional information about the center, the variation, and the shape, the distribution of the data for you to have a complete view of what the population of students at King's look like. So let's do some quick definitions first. Central tendency is the tendency to which all the data value groups around a typical or central value. Variation is the amount of dispersion or scattering of values. And shape is the pattern of the distribution of values from the lowest value to the highest value. And that's what I'm talking about how is the data grouped, what is in the center, what is on the side, and so on. The most popular measure of central tendency is the mean. It's the arithmetic mean. It's called average in some circles. It is the sum of all the values divided by the number of values. The mean is represented by x bar if it's the sample mean, and if it's the population mean, we use the Greek sign mu to represent it. The idea is that we take a sample, we calculate the mean, so we get the X bar, and we use that as an estimate for the population parameter. Usually we don't have an access to the whole population. What is the average height of individuals in the United States? That's the whole population. We don't have access to that information, so we do a selection from there, get a sample, calculate the height for the sample, represent that by X bar, and that gives us a forecast or a prediction for what the population equivalent will be. The mean is affected by outliers because of the way it's calculated, right? We've got 11, 12, 13, 14, and 15 here, and the mean is 13. Now, in the next data, we've got 11, 12, 13, 14, and 20. The mean is 14. We don't notice that gap, but 20 is an outlier. We might have more extreme outliers. I'll give you an example. Supposing we're calculating the average share price for a stock in the United States. It would be a travesty to include the shares of Berkshire Hathaway in that picture, because Berkshire is trading for something like $200,000-300,000. Most stocks trade for less than $1,000. $1,000 is pretty high. Apple is trading for about 130, Microsoft 200 and something, Amazon exception about $1,000. So Berkshire Hathaway at 300,000 is humongous. If you put that into a calculation for the average value of any group of stocks, the value that you get, the average you get, is too high to be the center of the data for most stocks and too low to be the center of data for Berkshire Hathaway. So in that picture, Berkshire Hathaway is an outlier, and we need to deal with it in some way. But the mean does not acknowledge the presence of outliers. The mean is also more accurate when the sample size is large and the sample itself varies less. So the variation is small and the sample size is large. Along with the mean being a measure of central tendencies, the median is also another measure of central tendency. In an ordered array, in other words, you order it from lowest to largest or largest to smallest, the median is the middle number. 50% of the data is below it and 50% of the data is above it if the data is odd. Now, if it is even, then it is the average of the middle two numbers. The median is not affected by extreme outliers because it's a measure of position. The value in the median for the first sample, 11, 12, 13, 14, and 15, the middle value is 13. Half of the data is below it, the other half above it. Again, when you have 11, 12, 13, 14, and 20, the median is still 13 because it's still the middle number. So it's not affected by extreme values on either side. The third measure of central tendency is the mode. It is the value that occurs most often. Now, we don't use the mode a lot because a lot of the data we use in statistics is continuous data and they all have decimal points. For example, 1.1 is not the same as 1.11 or 1.01. So mode is not used often, but there's some data that lends themselves well to mode. For example, if you have categorical data, rate your experience from 1 to 5, one of those numbers is going to be most popular, and the mode is the value that occurs the most often. What is your shoe size? Assuming that we have shoe sizes in whole numbers and they're standardized, then we will have a mode for that sample as well. The mode is also not affected by extreme outliers. We're simply counting the values that occur the most often. You can use it for numerical data or for categorical nominal data. Sometimes you have data that have no mode and you have data that have multiple modes. So first picture here, it has a mode of 9. 9 is the value that is most common. And the second sample has no mode. Every value occurs once. And now here is the interesting question. 3 measures of central tendency. The mode is not as popular, so we don't have to worry about it. But when you're summarizing your data, especially summarizing it for presentation, which measure of central tendency trumps? Well, it's back to what I said the first time. The mean is generally used. It is the most popular. It's easiest to calculate, period. So it's the most popular unless your data has outliers. If there are outliers in your data, then it may be more useful to present the median. If you notice, have you ever listened to housing news when they say the median house price in this state is this? It's because of the presence of outliers and the huge variation. The median allows you to peg the middle of the data so that half is below and half is above, rather than do the general average. So average is the most popular, is widely used unless you have outliers, in which case you repair the median. For most analysis, it makes sense to report the two, not for all. Again, for housing data, median might be adequate, but for most analysis, it makes sense to report the two. So, describing data with measures of central tendencies, then we move into measures of variations. How do we describe the width of the data, essentially, is what we're looking for. How wide is the data? How scattered out is it? There are 3 measures. We've got range, the easiest to use. We've got variance, and we've got the standard deviation. Measures of variation give information on the spread of variability or dispersion of data values. So if you look in this picture here, I've got the middle of the data. It's the same for these 2 data sets. Now, what I haven't said about this polygon you're looking at is that it's a graph straight out of some statistical package. So let's imagine it's Excel. What you have is X and Y, and then you have here you've got the frequency of occurrence of different kinds of values, and you have the values on the x-axis. So let's say this is 1, 2, 3, 4. 1, 2, 3, 4. Value 1 occurs once. Value 2 occurs twice. Value 3 occurs once. You end up with a graph that looks something like this. Now, I've oversimplified, but I'm just telling you the source of this chart or graph that you see here is just the frequency distribution of data. We take the data points and count them into buckets and end up with a nice little chart, right? So for these 2 charts, the mean of the 2 data sets is the same. But you can see from here that the larger one, the higher data set, has a smaller variation that data is in, whereas the one with the smaller middle, same mean, but is spread out a little bit more. Again, think about this line here as a number line. The range is the largest value minus the smallest value. Largest value minus the smallest value. It doesn't care what the distribution of data is. It's just looking at the difference between the two ends. What is the largest value minus the smallest value, which means that it is impacted by outliers. The smaller the number on one end and the negative end of the number line, the larger it is on the positive end of the larger line, number line, the wider the range is. And it really doesn't matter if it is if there's no variation, if it's an outlier, if it's far away from the rest of the data, it doesn't really matter. So here is a nice little picture. Range is sensitive to outliers. For the first sample here, all the data are evenly spaced out. The range is 5. The data is clustered and 12 on the other one. and there's nothing in the middle, the range is still 5. So very sensitive to outliers. More common measures of variation are S-variance and standard deviation. The variance is the average of the squared deviations of values in a set from the mean of the data. For example, supposing we have 3 data points, 1, 2, and 3. The mean of this data set is 3 plus 2 plus 1 is 6, divided by 3 is 2. So the mean, x bar, is 2. What we do with the variance is find the average of the distance of the data from the mean, the squared distance. So 1 minus the mean of 2 gives us minus 1. 2 minus 2 gives us 0. 3 minus 2 gives us 1. Again, I said the variance is the average of squared deviations from the mean. So we've got the deviations from the mean. We need to square that. The square of minus 1 is 1. 0 is 0. 1 is 1. So 1 plus 0 plus 1 is 2. So the square of the deviations right here is equal to 2. Now, the sum of the squared deviation is equal to 2. The deviations is 1, 0, and 1. So we need the average of the deviations. To do the average, we add them together and then divide it by n if it's the population variance we're calculating, or n minus 1 if it's the sample variance. In this case, we are doing a sample. 1, 2, 3 presumably is a sample from something. It just doesn't feel like the whole population of anything. If it was the whole population of anything, we will divide it by 3, but it's not. I think it is the sample, so we'll divide it by n minus 1. N is 3 minus 1 is 2, and that gives us a variance equal to 1. So let me go and I'm going to erase what I've written. You can pause it and have another look if you need some more time with it. But let's take the text here that describes what the sample variance is and match it to the formula here. So the variance is the average of the squared deviations from the mean. We start with the middle here, right here. The deviation of value xi, every single value. We call the values x, right? We name it x. So x1 is the value 1, x2 is the second value, x3 is the third value, fourth value, and so on. In our 1, 2, 3 scenario, x1 is 1, x2 is 2, x3 is 3. So every single x minus its mean. Then you square that. That gives you the square of the deviations. Then you find the average by summing all of the squared deviations and dividing it by n minus 1. Again, S is the sign for sample variance, S squared, whereas sigma squared, this Greek letter down here, is the sign for population variance. Usually when we do our analysis, we calculate the sample variance so that we can use it to estimate the population variance, amongst other things that we do with it. So there is the formula. What you need to know is the average, that the sample variance is the average of squared deviation of values from the mean. You divide by n minus 1 instead of n. If it's population, you divide by n. The standard deviation is the most commonly used measure of variation. When we did the variance, it's the squared deviation. It's the average of squared deviation. It's like, yes, the average of squared deviation in this sample is 3. It's not really easy to describe. The standard deviation is the square root of the variance. That takes our squared value and brings it back to normal terms. It brings back to the same measure as the data itself. So if you're talking about data in terms of percentages, let me use return on an investment and say, oh, the average return is 10%. Its standard deviation is 2%. Its variance is the square of that, 4%, right? Or we say the standard deviation is 4%. Its variance will be 16% because it's the square of the variance. So what we're saying in essence is that the average is 10, give or take 1, give or take 4. There are other ways to look at it. It gets a little bit more complicated, but essentially that's basically how you interpret the standard deviation. So it's most commonly used measure of variation. It shows variation around the mean, is the square root of variance, and has the same unit as the original data, and that is the biggest benefit of using standard deviation instead of variance. Computing standard deviation by hand, let me talk you through it once, step by step. When we get to class, we'll walk through how to do it in Excel. So step 1, calculate the difference between each value and the mean of the data. Square each difference. Add all of the squared differences together. Divide by n minus 1 to get the sample variance, and by n to get the population variance. Take the square root of the variance and you have the standard deviation done. Here is an example of how you would lay it out in Excel. It's not the only way, but certainly an example. So first, we've got all the x values in here. We calculated the mean as the average of all of the x values, and we have the mean down here. The first step then is calculate the deviation from the mean. 10 minus 16 is minus 6. 24 minus 16 is 8. Then you square that deviation in step 2. And then when you're done, you calculate the sum of that deviation and then divide it by n. That gives you the variance. You find the square root of that and you have the standard deviation. With standard deviations, smaller is better. The smaller the standard deviation of a data set is, the closer the data is bunched around the mean. That's what it is. If you think about the way we calculate standard deviation, is x minus its mean. So we're looking at the deviation of the values on average from the mean. So the smaller the number is, in general, the smaller the deviation is. So small standard deviation is better. Example is shown above. The first one, standard deviation is high. It's 3.338. Data B is clustered around the mean, so the standard deviation is less than 1. Whereas for the third one, the standard deviation is 4.567, giving us the fact that it is far away from the mean. Now, the third data set here, usually we want to use sample data to predict population data. And for you to see data that is so spread out in two different extremes like this, it's highly likely that the two data sets are from two different samples. So let me give you an example. Supposing I'm giving a test on statistics to King's College students. You would expect students that have taken my class before to score in the upper side of this distribution, and the students who have never taken it to score in the other end of the distribution, the 1 and the 12s. So the 1 and the 12s is probably people who have never taken the business statistics before, and 19 and 20 those that have, right? So you can't treat those samples as the same population. Well, for certain types of analysis you can, but if I'm looking at the probability that a student will pass my class, or looking at the performance of students in my class, then I should, in theory, consider these two groups separately and not just bunch them together. So again, smaller is better. And we're going back to the picture I showed you a while back with a sample that is wide and one that is small. The small and tall one has a smaller standard deviation than the larger one. What this means for the sample, I guess I forget to say that. Why do we care? Well, remember when I told you that we use the mean of the sample to predict the mean of the population? If the standard deviation is small, then we have more precise estimates. That's what it is. When we use the mean as a predictor, it means the margin of error is smaller. So we're done with measures of central tendencies and measures of variation. Now let's move on to measures of relative standing. One example of this is the percentile. The percentile is a number so that P% of the data falls below that value. So 90th percentile, 90% of the data is below it, 90% is above it. The median is the 50th percentile because 50% of the data is below it and 50th above it. We use percentile analysis when we're trying to gauge whether our data has outliers and for other things. But for now, understand that percentile is a measure of relative standing. Another measure of relative position is the z-score. It allows us to compare numerous data because the z-score expresses data in terms of standard deviations. A z-value of 1 means we are 1 standard deviation away from the mean. -1, we're 1 standard deviation below the mean. +1, 1 standard deviation above the mean. So z-score allows us to express data with different scales in terms of its standard deviations away from the mean. So I'm going to read. Z-score makes use of the mean and the standard deviation to specify the relative position of a number. The z-score expresses the distance between a given number and its mean in terms of standard deviations. So it's calculated as x minus the mean divided by s, which is the standard deviation. The first one is for sample, the second one is for population. How do I know? Because we're talking about mean in terms of mu, and we're talking about standard deviation in terms of sigma. So let me give you an example. Supposing I have a data set with a mean of 5 and a standard deviation. Actually, do you know what? Let's use numbers that are easy to work with. The mean of the sample is 4. The standard deviation is 2. If we have a number 6, we can work out that the z-score for 6 is 6 minus the mean of 4 divided by the standard deviation of 2. 6 minus 4 is 2 divided by 2 is 1. It's +1, positive 1. That tells us that the number 6 is 1 standard deviation above the mean. Supposing we have another data set. The mean of that data set is 10. The standard deviation is 5. We can use that data and formula to calculate the z-value, which is the value of 15, our x value is 15, minus the mean, which is 10, divided by 5 gives us a z-value of 1, which means that for both data sets, for the first one, 6 is 1 standard deviation above the mean. For the second one, 15 is 1 standard deviation above the mean. Right? That means if we know what the mean is and we know what the standard deviation is, we can recover the x value. The mean is 10, standard deviation is 5. We have a number that is 1 standard deviation above the mean. 1 standard deviation is 5, above the mean is 10 plus 5, 15. For the second sample, standard deviation is 4, standard deviation is 2, mean is 4. We have a number that is 1 standard deviation above the mean. 1 standard deviation is 2, plus the mean of 4 gives us the number 6. So we can always recover back to where we're coming from. Now, why is the z-value popular? The most one of the most common uses of the z-value is to figure out if we have outliers in our data. We define outliers as a number that is more than 3 standard deviations away from the mean. So in the first data set where the mean is 4 and the standard deviation is 2, 3 standard deviations is 2 times 3, 6. So a number that is 6 away from the mean and minus 6 on the other side away from the mean is considered an outlier. So 4 is the mean of this sample, plus 6 is 10, minus 6 is minus 2. So any number smaller than minus 2 or larger than 10 is considered an outlier. Now, don't ask me, because the 3 standard deviation thing, sort of arbitrary, but it makes sense in terms of probabilities. When we get to the chapter on probability, probably chapter 5, we will distill that information a little bit more. But a number that is 3 standard deviations away from the mean is considered an outlier in statistical terms. To compute the z-score of a data value, subtract the mean and divide by the standard deviation. The z-score is the number of standard deviations a value is from the mean. Very important to definition. A data value is considered an extreme outlier if its z-score is less than minus 3 or greater than minus 3. The larger the absolute value of the z-score, the further the value is away from the mean. That is to say, if the z-value is 1, if you compare that to something with a z-value of 3, then 3 is further away from the mean than 1. On the negative side, we also use the absolute values. So minus 1 is 1, minus 3 is 3. A number that is 1 standard deviation below the mean is closer to the mean than one that is 3 standard deviations below the mean. Here's an example of how you would use it. Suppose the average SAT score is 490 and the standard deviation of all the takers of SAT is 100. What is a z-score for a value of 620? It's 620 minus 4.490 divided by 100. That gives us a z-value of 1.3. Therefore, in this sample, the person that scored 620 is 1.3 standard deviations above the mean. It is not an outlier, it's just normal. We've talked about measures of central tendencies. We've talked about measures of variation. In there, we threw in a little bit of information about measures of relative position. So now let's talk about the shape of a distribution. The shape describes how data is distributed. For example, you might have a y-axis and an x-axis and a frequency polygon. In other words, you distribute the data and it looks like this, or it might look like this. There are more smaller data and a few really large data. It literally could look like this. Because this is just the frequency distribution chart. It has values on the x-axis and the frequency of occurrence on the y-axis. So it just shows you the distribution of the data, period. There are 2 useful shape-related statistics we look at. Just going to erase this. One is the skewness. It measures the extent to which data is not symmetrical. So this chart here gives us skewed data, whereas this one does not. Kurtosis affects the peak of the curve of the distribution. That is, it shows how sharply the curve rises approaching the center of the distribution. There is a normal shape. The top one, normal, most data sets follow this, but occasionally some data have more peaks than others, unexpectedly high peaks than others. How is this useful? When we are trying to use a sample to estimate the distribution in a population, we kind of need to know what the data in that population is expected to look like. We're doing estimation, don't forget. We have all the information about the sample. We don't know a lot about the population because nobody has the full population information. So in order to make assumptions about the population, you kind of, which is what we're doing in stats, right? You kind of look at the data, the sample, look at the distribution or make assumptions about the distribution of the population, and then you can make do some analysis based on that assumption. Very abstract. Bear with me, it will all make sense in time. Here are different types of shape, right? Skewness is telling us the extent to which data is not symmetrical. Here in the middle, let's start with what normal data looks like. And I say normal because mathematicians have done this, the statisticians have done this. They've collected data and then plotted the frequency of occurrence over time. And more often than not, most data follow this symmetric distribution. Certain data follows this left skewness, and a lot follow this right skewness. With the left skewed data, there's more observation on the negative side of the number line than positive. And usually I think stock returns follow that skewed distribution. So when data is symmetric, the mean and the median is equal. Remember, median slices the data in half. It measures the center of the data. Half of the data is above, half is below. The mean is another measure of central tendency that is helping us determine which value is in the center of our data. And when those two worlds collide, it gives us an indication that our data is symmetrical. For this class, all you need to know is that's our measure of symmetry. We assume that its mean and median is landing in the same position. Half of the data is above and below. Therefore, it is symmetric. Remember that if there are outliers, the mean is skewed. The mean is skewed. And data that is skewed does not look symmetric. So, what about left skewness? If we consider the numbers here a number line, this is the negative infinity side of the number line. This is the positive infinity line of the number line. That shows you that in this data, we have fewer smaller numbers and we've got a few small numbers, really, really small numbers, and more large numbers. When we have that, what happens is that the mean is skewed towards the small data. It's skewed towards the really tiny data. You've got, you've got 10 plus 11 plus 12, and then you have minus 52. The mean is going to be negative because the negative number is really, really, really small. And when that happens, when the skewness is towards the negative end of the number line, in other words, the tail of the distribution is towards the negative end of the number line, you have negative or left skewness. Think about this. Right hand. Oops. Okay. If you're looking at the screen, negative skewness is towards your left. It's not my left because I'm kind of, the camera is showing a mirror image of me. But if you're looking at the camera, if you're looking at your screen, the left side is towards your left hand, and that is left skewness. The right skewness is towards your right hand, that is right skewness. Relative to the mean, when you have right skewness, the mean is larger than the median. When you have left skewness, the mean is smaller than the median. Kurtosis, again, we have 3. If the kurtosis is 0, we have a bell shape or we have a normal distribution. If it's less than 0, it's flat. Greater than 0 is high. What this means is that you have more data in the center of your distribution than normal. Again, don't forget that we keep coming to this. This is a frequency distribution. And when the middle of your distribution is high, it means higher than normal. It means you have more data squeezed into the center than there is at the edges. If you're using Excel, here are the formulas for calculating all of the statistics. You can also use the data analysis tool pack. That we will walk through in class. But if you're looking for formulas for doing different kinds of things in Excel, there are some useful formulas. You can ignore the rest for now. Mean is average equals average. You select your data for house prices. You can practice with this page. Take the house prices, calculate the average. It's equal to, select all the data, and you have your average. Ignore standard error for now. It'll all become clear. The median that we've just looked over equals median. Select the data. Excel tells you what the median is. Mode, same thing, equals mode. Standard deviation. Now, back in the day, it used to be standard STDEV when you're calculating the standard deviation for a sample. Now, for a sample, you use STDEV.S. It's clearer, right? Because it shows you that there are 2 different kinds of standard deviations that you can calculate. One for a sample and one for a population. The .S version divides the sum of the deviation of the square deviation from the mean by n-1. Very, very important. The n-1 is a small sample correction thing, right? When you have a small sample, it will give you significantly different values if you use the .S versus the .P. Variance, you use variance.S for the sample version of variance and .P for the population version. You can calculate kurtosis by using Excel's Kurt. If kurtosis is greater than 0 or less than 0, you have some form of kurtosis in your sample that you have to account for. Skewness, if skewness is greater than 0 or less than 0, same thing, you have skewness. In this case, the skewness is positive 2. It means you have positive skewness. There are a few really, really, really large numbers that is skewing the statistics. And if you look here, I mean, 100, 300, 500, and 2 million. That 2 million value results in a positive skewness. Mean, you can calculate the smallest value using mean, the largest using max, and you can do sum or count as well. Now we can do other types of quartile measures. We've looked at percentile. Now we're going to look at quartiles. Quartiles divide your data into quarters. First quartile, you have 25% of the data below it and 75 above. The value that is the second quartile, don't forget, quartile is a relative position measure. It is the number that is in the middle of the data. 50% of the data is below it, 50 is above it. And the second quartile is the median. The third quartile is the 75th percentile. So let's go back. First quartile, 25th percentile. Second quartile, 50th percentile. Third quartile, 75th percentile. So just like the interpretation, 75% of the data is below it and 25 above it. Now, the quartiles that we calculated helps us divide data into pieces so that we can determine if we have outliers. If we have no outliers, the distance between the data in from the minimum value to the first quartile should be the same distance as between the first quartile to the second quartile, should be the same distance between you get the drift, right? Second and third. What that means is that the data is symmetric if the distance between the values are equal or roughly equal, right? So we calculate the different percentiles just to help us see if we have skewness. Now look at this. We have some skewness here. It may not be enough that it matters, but this data is certainly skewed. If you look at the distance between the minimum and the first quartile, it's larger than the distance between the other quartiles. So that tells you we at least have left skewness, aka negative skewness. Second way you can look at it is look at the middle 50% of the data. There's a lot more width here. The distance between the smallest and the largest value here is farther than here. So this data is somewhat negatively skewed or left skewed, but it may not be enough to matter. We'll look at how to check if it matters in a minute. There are 5 numbers that help describe the center of data, and I've talked about them in passing, but just to summarize, you need the minimum value, you need the maximum, and the 3 quartiles. That information helps us determine skewness. We've already used the median relative to the mean to determine if our data is symmetric, but we can also use this little chart here. If the median minus the smallest value is equal to the largest value minus the median, then it's equal distance, and we have symmetrical data. If Q1 minus the smallest value is equal to the largest value minus Q3, again, equal distance, our data is symmetrical. And same with median. If the distance is equal, it's symmetrical. If it's not, we start to vary into the left and right skewness picture. You don't need all of this information because you can read it by creating what we call a box plot. And a box plot is similar to what we had in the last slide. I'll expand on it more in a moment. The box plot allows us to visualize the distance by calculating Q1, Q2, Q3, smallest and largest, and just drawing that line that we had in the last chart. We can tell, right? In the last chart, I just looked at that diagram and I was able to tell if it was equal distance or not, if it was symmetrical or not, if I had skewness or not. Same thing here. So this table does exactly the same thing that we can do by looking at the chart. So here is your box plot. A box plot is a graphical display of data based on the 5 numbers summary. Smallest, Q1, medium, Q3, and largest. The median is Q2. When you draw the chart, if it looks like this, there is some skewness. The smallest value, the distance between the smallest value and Q1 is larger than the distance between Q3 and the largest value. Also, the distance between the median and the smallest value is also larger than the distance between the median and the largest value. That gives you a visual symbol. You don't need to memorize the rest of the table because you can see it. If data is symmetric around the mean, then the box and the center line is centered. Now, asking for data to be 100% symmetrical is asking for too much. I'm just going to put it out there. You are asking for too much if that's what you're waiting for. So the best we can do is approximately symmetrical. So if it's like this, then your data has no skewness. Here's an example of a box plot we created in Excel. Roughly symmetrical. The tail and the top. If you notice in Excel, the box plot that should lie on the side, it's lying this way. It's top to bottom, but you can see that this is the negative side of the number line and this is the positive side of the number line. So instead of lying on its side, Excel puts it up, period. And what you end up with is a visual representation. I can see from here that there's some positive skewness or right skewness in my data. There's some right skewness because the distance here is larger than the distance here. Now that skewness is not too much. It's reasonable. I want to say that it's going to be less than 1, just from experience. So if I was using this data, I'd probably assume this is what I would call relatively symmetrical. See the judgment call there? I'd make it. How do you compare the box plot to the polygon? They're exactly given the same information. Notice median of the data, Q2, Q2, Q2. The tail is what describes the distribution. This is the left tail, therefore you have left skewness. On the other side here, right tail, therefore you have right skewness, and the rest is symmetrical. We're done with samples. Well, not quite done, but let's go apply some of this to population. Numerical descriptive measures of population. Descriptive statistics discussed previously described a sample, not a population. Again, we took a sample and calculated all these measures about the sample. So it described the sample, not the population. Summary measures describing a population are called parameters. When you use it for a sample, it's called a statistic. Statistic is a summary calculation for a sample. Parameter is one for the population, and they are denoted by Greek symbols. So for sample, mean is x bar, variance is s squared, standard deviation is s. For a population, mean denoted by mu, variance sigma squared, standard deviation sigma. We're going to look at a table that lays it all out. Important population parameters, notice I keep going back to it, are the mean, variance, and standard deviation. Usually we care about what it is in the population because we are doing statistics and trying to figure out how it affects the average. Mu formula is exactly the same as for x bar. The only difference is here we're looking at the population, not the sample. Exactly the same. It's the sum of all the values divided by the number of values. Standard deviation, difference. For a population, you divide the sum of the squared deviation from the mean, you divide it by n. With a sample, you divide it by n minus 1. And notice when we're doing population variance, we are using population mean. And finally, standard deviation is just the square root of the variance. It's the most commonly used measure of variation. Again, it shows the variation around the mean, the square root of the population variance, and most importantly, it has the same unit. Variance is the square of the unit of observation, whereas standard deviation is the same unit as the data. Makes more sense. With one standard deviation above the mean, two standard deviations above the mean, easier to understand than when you use variance. Definitely easier to interpret. Now we get to empirical rule. The empirical rule is a rule about population of data. It came about from different experiments. Scientists have gathered data from large populations, and normally or on average, the data that is collected from any population at all is symmetrical. This is what we call a normal distribution. A symmetrical polygon is called a normal distribution. And it's called normal because that is normally the shape of all data in a population. The larger the data in the population, the more it exactly resembles this distribution here. So the empirical rule approximates the variation of data in a bell-shaped distribution. If we assume that the data from a population is normally distribution, and of course we don't know what the distribution is, we can assume. We don't have the population. We're making assumptions about the population based on what we know from the sample. So if we assume that a particular population S, I don't know, population of nurses' salary, population of student height, whatever that population is, if we assume that it is bell-shaped, then based on prior experiments, we can tell where most of the data in this population will reside. The empirical rule tells us what the distribution is. Approximately 68% of data in a bell-shaped distribution is within one standard deviation of the mean. Doesn't matter what the distribution is. 68% of all data in that distribution, if it is normally distributed, is between one standard deviation of the mean, within a z-value of 1 plus or minus 1. Let's extend the empirical rule. Approximately 95% of data in a bell-shaped distribution lies within 2 standard deviation of the mean. If you haven't caught on, bell-shaped is another name for normal distribution. So 95% of data will lie within 2 standard deviation, and extend that, 99.7% of data will lie within 3 standard deviation. So when we use the z-value of plus or minus 3 to designate outliers, what we are implicitly saying is that 0.3% of population data will be beyond that, will be considered outliers, but 99.7% of population data will be considered outliers. So 68% of all data in a population, if it's bell-shaped or symmetric, is within 1 standard deviation of the mean. 95% is within 2 standard deviation plus or minus 2. 99.7 is within 3 standard deviation plus or minus 3. We can start doing interesting things with what we know about the mean and standard deviation, and oh my God, the shape of the distribution. In this case, we're assuming it's bell-shaped and it's normal. Let's go see how this is used. Let's go back to the SAT problem. Suppose the SAT, the variable math score, is bell-shaped. So if you collect all of the math scores on an SAT and create a frequency table, the data is going to be bell-shaped. Let me help you out and draw something here. Frequency, numbers. So let's say we have something like, I know, let me do better. 200, 400, 600, 800. The mean of math score is 500. Somewhere here is where we have the mean. The standard deviation is 90. We can start to do some work here. 68% of all test takers. Now, if it's bell-shaped, by the way, the distribution is going to look something like this. Normal. And again, most data has a normal distribution. We find there are a few data that doesn't follow a normal distribution, but most data sets, dream it, think it, imagine it, call it, gather it, has a normal distribution. So safe assumption, if it's normally distributed, if the mean is, I'm going to erase all the numbers I have down here because right now only the mean is relevant. If the mean is relevant, if the mean is 500, 68% of all test takers will score between one standard deviation of the mean. We don't want standard deviation of the mean. So one standard deviation below the mean, standard deviation is 90. That's 500 minus 90 gives us 410. Above the mean, 500 plus 90 gives us 590. Because distributions are normal, we don't have to see it to believe it. We can assume normal distribution for the most part, because that's the shape of most data sets. I'll prove it to you when we meet up in person by just getting random data out of Excel and using it. I'll prove it to you. But essentially, it is bell-shaped. So 68% of SAT test takers will score between 410 and 590. 2 standard deviations above the mean is 2 times the standard deviation, which is 90. That gives us 2 times 90 is 180. 500 minus 180 is 320. 500 plus 180 is 680. So 95% of test takers will score 500 plus or minus 180. They will score between 320 and 680. Notice that the width is wider than the 68%. We know 68% will score between 410 and 590, a little bit precise. If we go further out, 95% will score between 320 and 680, and 99.7% of test takers will score between 500 plus or minus 270. So they will score between 230 and 770. And only 0.3% of test takers will score below 230 or above 770 in the math section of the exam. The empirical rule applies only to a distribution that we can assume is normal. If the data follows a normal distribution, in other words, you do a frequency polygon or you create a box plot and the data is normal, frequency polygon for the most part. If you create it and the data has a normal hump shape, it's a bell-shaped distribution, then the empirical rule tells you what to expect within one standard deviation of the mean. But if your data is not normally distributed, then we have to go with another rule called the Chebyshev's rule. Normal distribution if the data is normally distributed, otherwise use the Chebyshev's rule. Chebyshev's rule works regardless of what the population data is. If you think the population data is skewed, if you think whatever you think the population data is, height, for example, is not normally distributed, I don't think. I think there is some skewness in height in general in the population. If that's the case, you can't use the empirical rule to make assumptions about the distribution of data. You have to go with the Chebyshev's rule. Chebyshev's rule is 1 minus 1 over k times 100. K is the number of standard deviations. So regardless of how the data is distributed, at least 1 over 1 minus k squared times 100% of the data will fall within k standard deviations of the mean. Let's start with 2 standard deviations of the mean. 1 minus 1 over 2 squared times 100 is 75%. If the data is not normally distributed, you can assume that at least 75% of data will be within 2 standard deviations of the mean, and 88.89% of the data will be within 3 standard deviations of the mean. Less precise than when we do the empirical rule, because for empirical rule, 95% of the data is within 2 standard deviations of the mean. But if your data is not normally distributed, you cannot assume a bell-shaped distribution, and you therefore cannot use the empirical rule to assume the distribution of data. You have to settle for the Chebyshev's rule. Finally, I haven't talked about all the measures of dispersion or variation, measures of central tendencies, shapes, empirical rule, Chebyshev's rule. How do we look at the relationship between data? How do we look at co-movement of data? Because normally we don't study data in isolation. We study the co-movement of data. How is age related to development? How is age and height related? How is consumption and weight related? Normally we do analysis of data together. How is companies' stock return related to the stock return for the S&P 500? Two variables help us do that. First, if you want to visually look at the relationship between two variables, you use a scatter plot. The scatter plot allows you to visually examine the relationship between two numerical variables. But you also have two statistics that help you. Statistics or parameter, depending on whether you're looking at the population or the sample. If it's a sample, two statistics, the variance and the correlation. The covariance measures the strength of the linear relationship between two numerical variables. By calculation, it is x minus its mean multiplied by y minus its mean, sum that up, and divide by n minus 1. The covariance is only concerned with the strength of the relationship. We're measuring the deviation in x by the deviation in y and finding the average of that. For a sample, again, you divide by n minus 1. For population, I'm sorry, you divide by n, not n minus 1. There is no causal relationship implied. All we're saying is that one moves strongly relative to the other. When one goes up by 1, the other goes up by 1. Age and height are variables that I expect to move together. Calorie intake and weight, those are variables that I expect to move together in a positive direction. When your calorie intake goes up, your weight should go up. There are some variation depending on how your body burns fat or burns calories, how much exercise you do, blah, blah, blah. But the more calories you take in, on average, the more your strength grades up. So the covariance can help us measure the strength of movement within those two variables. Covariance only tells us the strength of the direction of the relationship. It doesn't really tell us how strong it is or how much it moves together. I kind of don't like this. This has been taken from the textbook. Let's say covariance tells us the direction of relationship. If covariance is positive, then it means that the two variables move positive relative to the other. When one goes up, the other goes up. When one comes down, the other comes down. If it's negative, then they move in opposite direction. When one goes up, the other comes down. So, again, if covariance is greater than 0, it's positive, they move in the same direction. If it's negative, they move in opposite directions. And if it is 0, they are both independent. It means the movement in one does not affect the movement in the other. Imagine if I was measuring my calorie intake and your weight. The covariance between those two variables should be 0 unless the relationship is spurious. In other words, it's just a 100% random event. But my calorie intake should not affect your weight. Those two variables are independent, but relative to my weight, there's probably a positive relationship. The covariance has a major flaw. It helps you determine relative strength. It helps you determine direction, but not the relative strength. You don't know if you're looking at two covariants for two different samples, you don't know which one is stronger. You can only tell that one is positive, the other is negative, because covariance is amplified by the size of the underlying data. The larger the data, the larger the calculation of covariance you end up with. The smaller the data, the smaller the value of covariance you end up with. So it doesn't really tell you that one is stronger than the other. It just tells you that they move in the same direction. So to remedy that, we use the correlation. Correlation is covariance divided by the standard deviation of the first value divided by the standard deviation of the second value. When you're calculating covariance, you've got to be very, very consistent. If your covariance is sample covariance, then you use sample standard deviations to divide. If your covariance is population covariance, then you use the population covariance, population variances to divide. The two numbers will give you the same thing, as long as you're consistent with the calculations and the inputs that you use. The correlation is between -1 and +1, or minus 100% and plus 100%. But I want to use minus and plus 1. If it's negative, of course, again, you have negative relationship. If it's positive, you have a positive relationship. 0 is no relationship. The larger the absolute value of the correlation, the stronger the relationship between the two variables. If correlation is 1, it's a one-for-one movement. When one goes up, the other one absolutely goes up by the same amount. If it's -1, then the same thing happens. You can 100% predict the movement in one if you know what the other value is, because it's 1-for-1 exactly. This one goes down, the other one will go down as well. The population coefficient of correlation is called rho. So correlation as a parameter is identified as rho. For a sample, it is R. So let's take a summary of what we've been doing with the Greeks and the values. Sample mean, population mean is mu. Sample standard deviation, population standard deviation is sigma. Sample variance is S squared. Population variance is sigma squared. Now we've got correlation, and that's rho. And sample correlation is called a signal as R. The correlation is unit-free. It's either expressed in decimals or percentages. It ranges between -1 and 1 when it's expressed in decimals. The closer to -1, the stronger the negative relationship. The closer to +1, the stronger the positive relationship. The closer to 0, the weaker the linear relationship between the two. So here it is. Correlation measures linear relationship between variables. Can you see? You can absolutely see this data, everything lines up on a straight line. It has a correlation of -1. Negatively, it's downward sloping. Upward sloping, correlation of 1. Here, it's spread out. They move generally in the same direction, but you can't predict the magnitude. So, correlation, this is a strong negative relationship. How do I know? We consider a correlation factor that is greater than 5 in absolute terms, greater than 0.5 in absolute terms to be strong, around 0.5 to be moderate, and close to 0 to be weak. So this one here is spread out, and it's a moderate to weak negative positive relationship. I'll say it's weak positive relationship, and this one here just signifies no relationship. If you plot the data as I've done in Excel, you can see it again. Take some time and spend on this slide. You can see what a negative relationship looks like in terms of its downward sloping. You can see what a positive relationship looks like, what strong and weak relationships look like. It's kind of very rare to find a correlation of -1 or +1, but you find everything that spans the gamut. In Excel, to calculate correlation, you use the Correl function. It needs two sets of data. You do equal Correl. Select the first set of data and the second set of data. The higher it is in absolute terms, the stronger the correlation. So the correlation between test score 1 and test score 2 is 0.34, positive, 0.73. What this tells you, if this was a score in my class, we'll call it a score for test 1 and test 2. It means that students that scored high on test 1 also score high on test 2. It's a positive relationship. So when one goes up, the other one goes up. If the relationship persists, I can assume that those who scored high in test 2 will also score highly in test 3. But for the information that I have, takers of test 1 tend to score high in test 2, and it is a strong positive relationship. It means that if I did this sampling in 1 year, and my students are typical, so the students who pass through my class year to year to year, typically they're typical, they look the same, then I can say that when I give my test again, students who do well in the first one are most likely going to do well in the second one because of the strong correlation between the two. Here is talking you through how we do this in Excel. In order to do this in Excel, you can use a data analysis toolpack or just run the formula. If you type the formula, it will work. But Excel has a data analysis toolpack that is not part of Excel as a matter of course. If you have a PC, click on File, scroll down to the bottom, you will see Options or More. If you see More, click on More, select Options. If you see Options, just select Options. Go to the add-ins. At the bottom of the add-in wizard, you will see Excel add-in. Click Go. It brings up a pop-up box, and you will see something like Data Analysis Toolpack, some other things, and Solver. Those are add-ins that come with Excel, but they're not loaded automatically. You have to load them in. So click on Data Analysis, click OK. When you go back to your spreadsheet, select the tab for data, the data tab, and it will be at the end, at the right, on the right at the end of your distribution. If you're using a Mac, I think you go to Tools, select Add In, and you should be able to see Excel add-ins. Click Go, same process. Select Data Analysis Toolpack, OK, and then go to the Data tab, and you will find the Data Analysis Toolpack there. The toolpack, if you select it, it shows you a bunch of wizards and functions and tools that Excel has prepared for you to do data analysis with. One of those options is correlation. Another one is covariance. Choose OK. Select your data, and it calculates the correlation for you. So input range, select both sets of data, not just the one you want, but both sets. I like to put labels in my data. So if you look here, I selected the box that says label so that it gives me information. So the input range is from A1 to B11, sorry. My data is in columns, it's displayed in columns. It has labels, and you can choose to output the data in a different worksheet or in the same worksheet. To put it in this same worksheet, you click on this radio box here, and then click in this box and just select one cell. I want to say F1. When you do enter, you end up with a table that shows you the correlation. Now, in that table, you have the correlation of test 1 with test 1, test 2 with test 2, and test 1 and test 2. What you need is the one for test 1 and test 2. Can I just say to you, right, that Excel gives you all the pairwise correlation for all the data you pass to it. So if you don't use the equal correl formula, what you will have to do is select all of your data, and Excel will give you the pairwise correlation for every single set data that you put in. You can do the same for covariance as well. If you investigate the data analysis toolpack, you'll find things like descriptive statistics, histogram, and other types of tools that we will go through as we go through the chapter. Here, the correlation for this data is 0.733, and we've interpreted it. Students who score high on the first test tend to score high on the second one as well. Here is the come to Jesus moment. Data analysis is objective. But sometimes the interpretation of it can be subjective. So when you come to interpreting data, you should do it in a fair, neutral, and clear manner. Don't mess with the data until it does what you want. For example, just arbitrarily going into your data and deleting all the outliers that you don't want might give you the answer that you want, but it's not representative of the population. You've messed with the data and created results that can't be applied to the population and also can't be objectively recreated. So you should report the summary measures in data as best you can, and then communicate the important aspect of the data. Interpret it, but communicate the data as is, and interpret with care and common sense. When you do statistics, one, you should document both good and bad results. You're not looking for the right answer. You are presenting the data that is, as is. If you work for a company and they ask you about certain things, should we go for this investment? If you take all the data you have, do some analysis and tell them yes, and you've done that analysis incorrectly, things may not pan out. And when they don't pan out, it will destroy your reputation. That's just the reality. So when you have results, try and be objective, present both the good and the bad. You should present it fairly, objectively, and in a neutral manner. And don't use inappropriate summary measures to distort facts. I remember going on the train once and looking at the statistics. 200%, the number of teenagers that are using drugs have gone up 200% in the last year. 200% is alarming, right? But in that advertisement, I don't have an idea of what 200% means in terms of numbers. Was it 1 and now it's 3? Was it 2 and now it's 6? Like, was it 100,000 and now it's 300,000? Like, you need to give context for the presentation of the data. It's not enough to pick the data that is just headline or attention grabbing. Consider that. So in this chapter, we've talked about measures of central tendency, arithmetic mean, the median, and the mode. Mode, most likely value. Median, the number of value in the middle of the distribution. 50% of the value is above, 50 below. The mean is the average, is the sum of all numbers divided by n. We also talked about measures of distribution. The more data is spread out, the larger the range, the variance, and the deviation. In other words, all of the measures of variation are larger, the larger your data, the wider your data is, the more spread out it is. And by Extension, the more concentrated your data is, the smaller all of those values are. If the measures are all the same, then there is no variation in your data. All of these measures will be zero. Range will be zero, covariance will be zero, standard deviation will be zero. Range, variance, and standard deviation is never negative. The range is largest minus smallest. Worst case scenario, it's zero. Standard deviation is the square of deviation. That's the starting point. Square of anything is positive. And the square root of a positive number is positive. So they're never negative. If you do a calculation and it comes out as negative, you, my friend, have used the calculator incorrectly. We also talked about measures of distribution. One was skewness. This is a histogram of different types of data. Here, the data is right skewed or positively skewed. Here, data is symmetric, you can see. And down here, data is negatively skewed or left skewed. You've got to know all of the names because I will be checking for name definitions as well. Left skewed or negatively skewed, right skewed or positively skewed or symmetrical. Again, the tail describes the skewness. The tail is in the direction of skewness. We talked about kurtosis. This data has a kurtosis less than 1. There's really no peak. This data has a kurtosis that is greater than 1, positive kurtosis. We have less data on the ends and much of it in the middle. We also talked about the relationship between the polygon or data charts and the box plot. The tails are in the same direction, and the box plot will usually tell you the same thing that the polygon tells you. We talked about the Greeks and the equivalent for sample statistics. So mean is X bar, population equivalent or parameter is mu. Standard deviation is S. The population equivalent is sigma. Variance is S squared. The population parameter equivalent is sigma squared. We also talked about the empirical rule, one of the most important rules because we use it to calculate probabilities. If 95% of the data is within 2 standard deviation, we sort of can work out the probability of getting a certain number from a population. We'll get to that in chapters 4 and 5. Empirical rule, 68% of data is within 1 standard deviation of the mean. 95% of data is within 2 standard deviation of the mean, and 99.7% of data is within 3 standard deviation of the mean. Covariance and correlation is a measure of relative movement, co-movement between data. Positive covariance means there's positive movement. When one variable moves in the positive direction, the other moves in positive direction. When one goes in the negative direction, the other also moves in the negative direction. So they co-move in the same direction if the covariance is positive. If the covariance is negative, they co-move in opposite direction. When one goes up, the other goes down, and vice versa. Covariance only gives you information about the direction of movement, not about the strength of the movement within data. Correlation steps in to tell us about the strength of the relationship. The movement is lined up if correlation is really, really high. And in absolute terms, the lower it is in absolute terms, the more spread out the data is. So The higher the correlation, the better your data is at prediction. It means that if you know what happened to Y, you can predict what is going to happen to X. And here is a summary of chapters 2 and 3. It gives you how to present and calculate variables. Qualitative variable, if it's one variable summary versus two variables, it tells you the types of tables you can use and the kinds of graphs that you can use for a one variable or two variable analysis of qualitative data. For quantitative data, you have a little bit more. You can use the dot plot. You can use stem and leaf display. You can use histogram, box plot, and polygon. I have a weakness for histogram, box plot, and polygon. I think I should rephrase that and say I have a preference. You can do analysis for numerical descriptive measures. You look at measures of central tendency, measures of variation, and measures of relative standing. I've missed out the quartiles there, but quartiles and percentiles are related. And so this gives you a visual of most of what you can do with it. This is the end of the class. These are practice problems for you. If you wanted to practice, go to the textbook for the class and just practice with these problems. This is the point where I say any questions, but I'll save your questions for when we meet in person. Enjoy the rest of your day.